When we learn about Laplace transformations in an introductory differential equations class, the main motivation is that they give an efficient way to solve differential equations of the form y double prime plus by prime plus cy equal f of t, where f of t is a piecewise continuous function. Second-order differential equations like this arise in applications of Newton's second law of motion, so we sometimes refer to f of t as the forcing term. Another kind of forcing term is an impulsive force, which comes about when an object is dealt an instantaneous hit, like a stick on a drum or a piano hammer on a string. The theoretical physicist Paul Dirac defined such a function in the early 20th century, which we call the Dirac delta function or the impulse function. The main properties of the Dirac delta function, delta of t, are the function is zero except where there's an instantaneous spike, so delta of t minus a is equal to 0 for t not equal to a, and the spike for delta of t at t equal a is so large to cause the area under the entire function to be equal to 1. So the integral from negative infinity to infinity of delta of t dt is equal to 1. One thing that we need to observe is that if the function is 0 everywhere except at t equal a, then the integral should be equal to 0. But this is why we say the spike is so large, because essentially we are implying that the spike is infinitely high at that point. Another observation is that delta of t can be thought of as the derivative of the unit step function, which changes from the horizontal line y equals 0 to the horizontal line y equal 1 at t equal a. The derivative of this function is 0 everywhere except at t equal a, at which point the rate of change is so fast it is infinite. For the purposes of solving differential equations, it can be shown that the Laplace transformation of the Dirac delta function is L of delta of t minus a is equal to e to the negative sa. Since we've already seen how delta of t relates to the unit step function, it should be no surprise that for differential equations where the force term is an impulse function, the solutions involve the unit step function after taking the inverse Laplace transform. And finally, it can also be shown that for a continuous function g on negative infinity to infinity, that the integral from negative infinity to infinity of g of t delta of t minus a dt is equal to g of a. What we have defined here for delta of t is not really a function in our familiar sense. It is a distribution. This means delta of t is only defined in terms of what happens when we multiply it by a function and integrate, which is what we've seen with this integral. Related to this integral is another problem that can arise with Laplace transforms, taking the inverse Laplace transform of an expression of the form h of s equal to f of s g of s, where the inverse Laplace transforms of f of s and g of s are known. To determine the inverse Laplace transform of such an expression, a convolution product is needed. If f and g are continuous on the interval 0 to b, then for t in the interval 0 to b, the convolution product f star g of f and g is defined by f star g of t is equal to the integral from 0 to t of f of t minus tau g of tau d tau. The integral in this definition is called a convolution integral. And if f and g are an e of 0 to infinity, then the Laplace transformation of the convolution product f star g is equal to the Laplace transformation of f times the Laplace transformation of g. And this gives us that the inverse Laplace transform of f of s g of s is equal to the convolution product f star g of t. We can use these results to solve some differential equations, but now let's turn to where these ideas have shown up in audio recording. The first concept is that of an impulse response, where a sound, the impulse, is played in a space and a recording is made of the space's response. For example, we could stand in a room, clap our hands once, and then record the response of the room, which really means capturing the acoustic ambiance of the room. We could also use a sustained sound, like a sine wave that sweeps through the audible frequency spectrum from about 20 Hz to 20,000 Hz. Why would we bother recording these impulse responses? If we consider the scenario of sweeping a sine wave through the audible frequency spectrum, we are capturing what any sound would do in that space, since all sound can be decomposed to sums of sine waves. What we can then do is convolve this impulse response with an audio signal, which essentially amounts to the multiplication of their frequency spectrum. If we take an audio recording of anything, say a dog bark, and then convolve it with the impulse response of the room we clapped our hands in, then we would get the sound of the dog barking in that room. These concepts have led to the ability to digitally model a setup of a guitar amplifier, speaker, and microphone configuration so that a guitar player could capture their sound in a studio and then use that same sound when they play live in a stadium. Additionally, convolution reverbs are hugely popular since any recorded sound can be made to sound like it was recorded in famous concert halls and studios around the world. The program I use to record, Logic, has reverbs that can make it sound like I am at a studio in Berlin or in a nuclear reactor. Paul Dirac may not have guessed this is how his theory would have been used, since digital technology didn't exist, but it is a powerful application of his function that is widely used in audio design today.